Okay, so in this video we're going to go ahead and take a look at the motion of a body with variable mass. Now, this is a problem that we've already treated several chapters ago, partially, and so we'll pick it up some more here. So let's look at an accumulating raindrop as it falls down. So as it falls down, it's falling, its mass is m of t, it's falling with velocity v of t, and it's going to run into a little particle of water, mass delta m, going at u of t. So we'll let big V equal u minus v. So this is the velocity of the fractional mass with respect to the raindrop. So we'll go ahead and look at their collision. The change in momentum will be, well, afterwards it's going to be moving at m plus delta m. It's velocity v plus delta v. That's the final. And the initial is, so just continuing over, the initial is mv, whoops, plus delta m u. Okay. So we can group that around a bit. So you get that delta p is equal to m delta v plus delta m delta v minus delta m times u minus v, which we recognize as being big V. Okay, so finally we can put it all together and get that it is m plus delta m times delta v, whoops, minus delta m times big V. Okay, so we did that for an accumulating raindrop, but we could just as easily do this the other way around. And imagine that we were shedding off mass. For instance, if it was a rocket burning, that's just going to change some signs. So anyway, if this is my small time, my change in momentum for some small time period, we can transition this to a derivative. So dp dt would be equal to m v dot from here minus m dot v. Okay, and that has to equal our external force. So we've already seen for the case when the external force was 0 that we got that v equaled v naught plus big V times the natural log of m naught over m. Okay, but now let's look at a case where the external force is non-zero. All right. So in that case, we have m times dv dt minus big V times dm dt will now equal mg, say if it's gravity. And I will choose up to be positive. So then This will give me m dv dt going into just the y coordinate. Now, this is a minus here, but the relative velocity of the exhaust is down for our rocket. So we get plus v dm dt equals, and the force is down, minus mg. All right. So working to solve this, I can get m dv plus v dm equals minus mg dt. All right. First things first, we want to get a final velocity, so let's separate that out. So this is equal minus v dm minus mg dt. Okay, so if we divide through by little m and by big V both, I will get dv over big V is equal to minus dm over m minus g over v dt. So if we're going to have a lift off, excuse me, we're going to require that minus dm over m, and keep in mind our differential of mass is going to be negative because we're losing mass as we burn our rocket, has to be greater than g over v dt, or we're just plain not getting off the ground. So this g over v is the beginnings of a good figure of merit. We define the specific impulse of our engine, tau s, to be v over g. So the bigger the specific impulse, the easier it is for the rocket to lift off. So if we go ahead and integrate our rocket equation here, it's going to become, we're going to get 1 over v, and we're just going to integrate from 0 to v final dv. Okay, that's easy enough. Equals minus, for the mass term here, we'll be integrating from the initial mass to the final mass, dm over m. Okay, and now this is 1 over the specific impulse, and we'll be integrating from 0 to the burnout time dt. So this is the burnout time right here. In other words, how long did the rocket fire? Okay, so we can do those integrals. This will be v final over our exhaust velocity. This will be the natural log of, actually we can get rid of the minus sign. This will be the natural log of m naught over m final. And then here I'll have minus the burnout time over the specific impulse. And sadly, rocket technology really hasn't changed too much since the 1960s. So these numbers are pretty solid. The typical value for the specific impulse is about 300 seconds. And a typical value for the burnout time is on the order of 600 seconds. Typical. So looking at that, since we're subtracting 2 here, the natural log of the mass ratio better be bigger than 2 just to have a meaningful final velocity. So to have a meaningful v final, you need m naught to be, demand that m naught be greater than or approximately 5 times the final mass of the rocket. So at least 4 times your payload of mass is going to be fuel just to even really get moving. And then the book shows that, say, to put something to low Earth orbit, like say to the International Space Station or something like that, your fuel to stuff ratio is probably more on the order of like 27 to 1. And that's just to get to low Earth orbit. If you want to go significant distances, like say to or past Jupiter, you're going to have to work a lot harder. So there are 3 ways to Jupiter. One way you could do is by brute force. That's kinda not quite what they did with the Voyager satellites. They had a good alignment of the outer planets. So you can stick a small payload on top of a very large rocket, and you can barely make it to Jupiter by the shortest route. Perhaps the most clever way is some form of ion drive. The usual idea here is that you accelerate xenon atoms, just because they're the most massive neutral atom you've got. So 1/2 mv squared. So that's the kinetic energy of one of your exhausted particles, is going to equal the charge. Usually you can strip 1 electron off of the xenon times the electric potential, which I'll call phi, just not confuse it with the v we already have. So you can see for whatever acceleration potential you have, the bigger the mass, the happier you are. That's why we like xenon. So we get an exhaust velocity of root 2e phi e over m. If we put in for a typical value for xenon, so it's 2 times 1.6 times 10 to the negative 19 coulombs. One of the early attempts at this was a satellite called Deep Space One. It used 1280 volt accelerating potential. That's gotten better since, but we'll just use this for funsies. Mass of the xenon atom is 2.17 times 10 to the negative 25 kilograms. Crunch it all through, you get 4.3 times 10 to the 4 meters per second. So the specific impulse of our ion drive is v over g, so putting that in, 4.3 is 10 to the 4 meters per second over 9.8 meters per second squared, you get 4,400 seconds. Yowza! That's a lot better than our previous, typically about 300-ish or so. Now, that's sort of like a good theoretical number. The reality is more along the realm of 1900 to 3200 seconds for that particular satellite. Anyway, it's about 10 times the specific impulse of a Saturn V rocket. That sounds really awesome. One downside, though, the thrust. It turned out to be 0.114 newtons. So, problem is you can't get it off the Earth. The thrust is too low. So the trick is you go ahead and stick the satellite that has a engine like this onto some typical launch vehicle, like say a Delta V, a Falcon 9, whatever. You maybe, depending on what you're doing, you might even piggyback it onto some other mission. And then once you get it off the Earth, then you can switch over to the ion drive. Well, those are 2 approaches. The most common one, though, involves using the slingshot effect. So the idea goes like this. Just go fly by a planet. Any planet will do. So you're coming in. Here's your satellite, mass m1. There's your planet, mass m2, moving at velocity v2. This is going to come in at v1 and leave at hopefully a much bigger v1 prime on the way out. And obviously the mass of m1 is a lot less than m2. Now it's an elastic collision, so we have that v1 minus v2 equals minus v1 prime minus v2 prime. But since m2 is huge compared to m1, we saw that that gives us that v2 prime is going to be basically v2. So that gives me v1 prime, solving here, be equal to minus v1 plus 2v2. So the moral of the story is that by swinging by a planet, you can gain up to double the planet's speed for free. And in fact, you can do even better than that. If you go ahead and fire your rockets at the same time, right, then you've made yourself a nice spiffy endo-ergot collision, and so you can pick up even more speed. And in fact, that's often what's done. But anyway, if you're sending something out to the outer solar system, usually the way the missions are rigged up, you have it make several flybys of planets in the inner solar system to pick up speed. Then you finally have enough speed to be able to make it to Jupiter. And then don't forget, you're slowing down as you head away from the sun due to the sun's gravity. Then either, if you're looking at Jupiter, great, you go into orbit around there. Otherwise, you fly by Jupiter and pick up a boost off of Jupiter and then go to wherever it is you're going. Okay, and Jupiter is a really good segue for what will be the next video, which will be looking at the restricted three-body problem. We'll get to visit Jupiter's Trojan satellites and also the Kirkwood gaps in the asteroid belt, which are due also to Jupiter.